The real world is messy. Emails can look suspicious without being spam. Medical symptoms can point to more than one condition. A photo can be blurry, cropped, or taken in bad light. So here is the main question. How can machine learning make predictions when the world is uncertain, noisy, and incomplete? A model never sees the whole real world. It sees data, examples, patterns, measurements, and signals. Because the evidence is incomplete, the answer is usually not absolute truth. It is a probability. Here is an email. The model reads the words, the links, the sender, and the formatting. And instead of saying, "This is definitely spam," it says, P of spam given email features equals 0.95. That number is the doorway into this chapter. Machine learning is not only trying to be right, it is trying to measure how likely something is, given what it knows. Now we give that number a name. Probability is a function. It takes an event and assigns a number to it. P of A here, A is an event, and P of A is the probability of that event. For example, P of rain equals 0.30 means there is a 30% chance of rain. Every probability must live between 0 and 1, 0 less than or equal to P of A less than or equal to 1, and the probability of the whole sample space is 1, P of omega equals 1. That means something in the set of all possible outcomes must happen. One very useful rule follows immediately. The complement rule, P of A complement equals 1 minus P of A. So if P of spam equals 0.95, then P of not spam equals 0.05. This is already the beginning of binary classification, one class and its complement. Once we can assign probability to one event, the next question is, what happens when we combine events? For A or B, we use the addition rule, P of A union B equals P of A plus P of B minus P of A intersection B. The subtraction matters because the overlap gets counted twice. Imagine a customer who might buy coffee, cake, or both. The probability of buying at least one is the coffee probability plus the cake probability, minus the overlap where both are true. For events happening together in sequence, we use the multiplication rule. P of A intersection B equals P of B given A times P of A. Read it as the probability of A and B together equals the probability of A times the probability of B after A is already true. This is the bridge to Bayes' theorem. Now the vertical bar becomes important. P of A given B means the probability of A given B. Mathematically, conditional probability is P of A given B equals P of A intersection B divided by PB. This says once B is known to be true, shrink the world down to B. Inside that smaller world, ask how much also belongs to A. That is exactly what a spam filter does. It does not ask only P spam. It asks P spam email features. When the email contains free, many links, and an unknown sender, the model updates its belief. P of spam given email features equals 0.95. Conditional probability is the mathematical version of given the evidence. Bayes' theorem should not feel magical. It comes directly from conditional probability. Start with P of H given E equals P of H intersection E divided by PE. Here, H is a hypothesis, like the patient has the disease. E is evidence, like a positive test. Now rewrite the joint probability using the multiplication rule. PH intersection E equals PE HPH. Substitute that into the first equation. PH E equals PE HPH over PE. That is Bayes' theorem. It says, start with a prior belief, measure how likely the evidence is under that belief, then normalize by how common the evidence is overall. This is how probability updates when new evidence appears. So far, probability has been attached to events. Machine learning also needs variables. A random variable turns uncertain outcomes into values. For a coin, x equals 1 for heads, x equals 0 for tails. In machine learning, features and labels can be treated as random variables. A probability distribution tells us how probability is spread across possible values. For a die, the distribution is discrete. Each outcome from 1 to 6 has probability 1/6. For measurements like height, noise, or prediction error, the distribution may be continuous. One famous continuous shape is the normal distribution or bell curve. Another powerful idea is expected value. E of x equals sum over x of x p of x. It means the long-run average. For a fair die, the expected value is 3.5. This idea will matter later when we talk about loss functions and optimization. Real machine learning data usually has many variables at once. Joint probability keeps variables together, P of A, B. For example, the probability that a user clicks and buys. A probability table lets us see those combinations as cells. Marginal probability zooms out. P of A equals sum over B of P of A, B equals B. That means we sum across the other variable and keep only the one we care about. This also gives us a clean definition of independence. If A and B are independent, P of A, B equals P of A times P of B. But in machine learning, features are often not independent. P of A, B not equal to P of A, P of B. Income and education, symptoms and disease, words and spam labels. Useful signals are often connected. Now the whole chapter connects to supervised machine learning. Most supervised models can be viewed as estimating P of Y given X. Here, X is what the model observes. Features, pixels, symptoms, transaction details, or email content. And Y is what the model predicts: spam, cat, fraud, disease, or any class label. Examples: P of spam given email, P of cat given pixels, P of fraud given transaction, P of disease given symptoms. The model is not seeing the whole world. It is using the evidence in X to estimate the probability of Y. That is why probability is not a side topic in machine learning. It is often the shape of the prediction itself. Now the chain is complete. Probability starts with events. P of A. Then we learn complements, addition, multiplication, conditional probability, and Bayes' theorem. Random variables let us attach probability to values. Distributions show how probability is spread. Expected value summarizes the long-run average. Joint and marginal probability help us work with many variables at once. Independence tells us when variables do or do not carry information about each other. And machine learning brings the whole chain together as P of Y given X. Based on the data I have seen, this outcome is more likely than that one. That is the language of uncertainty in machine learning. And it leads directly to the next chapter: probability distributions, the patterns behind data. Thank you for watching. In the next chapter, we will look deeper at probability distributions. Stay curious and keep building your machine learning foundations.